Okay, this is going on page 106 when we're done. So yesterday we plotted points in the polar coordinate system and we converted from polar to rectangular and vice versa. So today we're going to look at some of the graphs. And for polar functions, the inputs are given by theta, which is your independent variable. Outputs are given by r, which is your dependent variable. And our ordered pairs look like this, r, theta. So we are used to x, y, where x is your input, y is your output. But with r theta, theta is your input and r is your output. So they're switched around. Okay? But it really doesn't matter kind of which one you do first. I want you to make sure you think about your input and output and how that works. So on the exam, because I know sometimes the wording is what throws y'all off, if they give you an equation, the wording might look something like this. The graph of a polar function, r equals f of theta, instead of f of x, where f of theta, remember all that is r, equals 3 minus 3 sine theta, is shown in the polar coordinate system for 0 to 2 pi. So it's giving me a domain restriction, because since it's on a circular grid, we could keep going in circles and go around, and we don't want to always do that. All right? So we're going to start off by graphing one together. But before we do that, let's jump to the bottom, because I want to read this first, actually. On the AP Pre-Calculus exam, polar functions will only appear in the multiple choice questions. This means that students will not be required to sketch polar functions by hand. However, students will be expected to understand polar functions, their graphs, and what portion of the graphs exist, blah, blah, blah. Now, you're also not going to be required to graph sine and cosine functions, right? But if you can't graph those on your own for yourself today, then it's going to make some of this other stuff confusing. So even though you're not required to, you still have to have an understanding of them, all right? So that's why we're going to start off by graphing one together. And we're actually going to start down here because I'm going to rewrite what that says up there because I can't see it from up there. So this is f of theta is equal to 3 minus 3 sine theta. Okay, I'm just rewriting it because it's up there and I can't see it. All right, so I need to have an understanding of what this looks like in the rectangular coordinate system. Now, if I was to actually convert this equation to the rectangular form, which is something that we could do, but we're not going to be required to do, then if I graph this in polar and the other one in rectangular, the graphs should look exactly the same. We're going to graph something, but that's not what we're doing. What we're doing is saying this looks very much like an equation that we understand. If this was y and this was x, we totally understand how those work. You agree with that? So we're going to graph. So we need this here. And then we know the sine parent function looks like this. All right, so tell me, what is the vertical translation of this function in the rectangular coordinate system? Vertical. 3, because that would be this right here. That's the D, right? So 1, 2, 3. That means that's where my midline is. Let me make it look more like a midline. I'm just going to dot it. Okay, what is my amplitude? 3. Amplitude is 3, so that means from my midline I have to go up and down 3, so make my little hash marks there. And then it is negative, but what does that negative do? It reflects it. Okay, so let's plot this, and it's really not making this beautiful and perfect, but we are doing a little bit more than we normally do with our ugly sketches, okay? So I know that sine starts on the midline at the y-axis, like right there. I also know it ends on the midline. And I know that halfway between the two, I'm also on the midline. Something like that. Then, usually, I go halfway between these two zeros, and I go up whatever the amplitude is, but because of this reflection, halfway between these two, I'm going to go down 3 and be at 0. And halfway between these two, instead of going down, I'm going to go up 3 right there. So this is what my sine function looks like in the in the rectangular coordinate system, okay? Then we're going to use this to help us graph it in the polar coordinate system. Okay, everybody okay with this graph so far? Now, tell me, what is the period for sine? 2 pi. So I know that this is at 2 pi. Is the period for this function also 2 pi? What affects your period? A, B, C, or D? B. What is B in this function? 1, right? B is just 1. So that means that this is 2 pi. This is 0. This is 2 pi. So halfway, this right here is pi, which makes this pi halves, which makes this what? 3 pi halves. Okay. And so we're going to look at not only the polar stuff, but the connection between the rectangular and the polar graphs. We're going to start by filling in some of the things on this chart. So from the graph that we just graphed, I know that when the angle is 0, the output is what? 3. So when theta is 0, r is 3. When else is the r value 3? Pi and 2 pi. Okay. What is the r value at pi halves? 0. And at 3 pi halves? 6. Okay. Now all these values that we have not filled in, we could get by substituting in these other angles as they go down here, right? But if we did that, which we totally can, I'm going to get a lot of answers with weird square roots in them, and then that doesn't help me when I'm trying to estimate things, right? So I'm just going to give you the other numbers. I want you to understand that they're coming from here, but I'm just going to give you the other ones. But before we do that, every single number we write in there now, what it has to be true about all of them? What's going to be true about all the numbers we write in there based on this? Well, yes. They're all positive, right? All my y values are positive, okay? Except for that one that's a 0, but we already have him up there. If this equation, if this was a 2 and not a 3, I wouldn't shift up as far, and part of this graph right here would be underneath the x-axis, which means I would have some negative numbers up there, okay? See how all that works together? All right, so let me just give you the other numbers and fill them in, and then we'll go from there. This one is good. Pi 6 is 1.5, then 0.878, 0.401, 0.401, 0.878, 1.5, and then 4.5, 5.121, 5.598, 8.121, 4.5. Okay, so get those filled in. All right, so remember that this is my theta, this is my r, but my ordered pair is r theta, right? Then we're going to label just the angles in the first quadrant just to help us out, because sometimes looking at all those lines, they get a little weird. So halfway between 0 and 2 pi, I know that this would have to be pi fourths, which makes this pi sixths, and this pi thirds. And then we don't really care about these, but that would be pi 12ths and 5 pi 12ths. That's something you could figure out if you absolutely had to, but they're just there to break this up all evenly. All right, so we're going to plot these in a specific order. My radius for my first ordered pair, which is 3, 0, my radius is 3 and my angle is 0. So one thing I didn't realize till I copied this is that I don't really like the scale, because they're not counting by 1s or 2s, they're counting by weird stuff. So when I have to go to 3, 3 is halfway between 2 and 4, which isn't actually on a line, which makes the other estimation a little weird, but we can do this, because we can do hard things. All right, so then I'm going to go to pi sixths, and I got to get 1.5. All right, well, halfway between 0 and 2 is right here, And then halfway between those two would be kind of right there, except can't always hit what I'm trying to hit with. Kind of right there. Well, 1 is right there, and then halfway between that and that, that's where you end up. You got to do half and half. Then pi fourths is 0.878. So I'm going to go to where about 1 is and go a little bit less than that. Pi thirds, I'm going to find 1, go to about half of that, a little bit less. I'm like right there. Maybe a little bit less than that. It's hard for me to hit with this pen. And then at pi halves, I'm at 0. So what we have just done, and I have to scroll a little bit since my recorder's in the way. What we have just done, those that we just graphed, that is this part of the graph right here. We just went from 0 to pi halves. Those are the points we got on here. Okay? Then we're going to keep going. So at 2 pi thirds, I'm going to be at about 0.4. At 3 pi fourths, I'm at about here. And at about, or at 5 pi sixths, I'm at about right there. And then at pi, I'm at 3, which once again is weird, and it's right there. And notice there's symmetry. That can help you kind of line them up. Just like there's symmetry on this graph, because we did this part, now we did this part, right? That's symmetric. That's symmetric to that right there. See that? All right, everybody with me so far? So now we're going on to 7 pi sixths, 4.5. So 7 pi 6 is right here. So halfway between 4 and 6, 5's right there, so 4.5 would be right about there. 5 pi fourths, a little bit more than 5. 4 pi thirds, probably about like that. And then 3 pi halves at 6. And then we just plotted that part. And just like the other, there's symmetry. So you have those points. Once you get those on there, you can just use your symmetry to get the other ones on there, which might be a little bit easier, especially with the weird scale. Something like that. So it looks nothing like our rectangular one did, but like I told you from the beginning, it wasn't going to because we didn't convert. We were just looking at it rectangularly. And we're going to draw this in the order that we graphed it. We started here. We plotted those points. Then we plotted those. Oh, I have to kind of stand in front, sorry. Then we plotted those points. Then we went around here and hit all these to get that. It's a heart. So this is actually called a cardioid. Like cardiac, like heart, cardioid. Okay. So that's one of our many polar graphs. Now, like I said, you're not going to have to plot one again, but I wanted you to see how the plotting works. And I'm going to show you a better little example of how they're tied together from this. Okay, so on this, on the right-hand side, it's going to graph it, the rectangular version of it. Here, it's going to graph the polar version of it, and it's also going to graph a little circle, and the circle is just there to show you how much of the unit circle we did. So if I go from 0 to pi halves, see the blue part? That's just saying literally on the unit circle, we went from 0 to pi halves. But this was the first part of those points that we plotted. That's the first part of my sine function. Then I'm going to go pi halves to pi. This is symmetric, and so is that. And then I just keep going, and that's how that gets drawn over there. Okay, this is the rectangular version. That is the polar version. Okay? And it looks much better than what I just graphed for you. So, all right. So like I said, you're not going to ever have to in here anyway, ever have to graph them again. But there are some things that we need to know about them. And let's see, let me point this out too. So it does say it's very common for polar functions to display symmetry. So if you know what it's supposed to look like, you can get some symmetry there, and we can use our understanding of symmetries. All right. So flip it over. Take a look at this chart of these basic classic curves. We're going to look and talk about each one of these. We're going to write down how they're related and what's important about them. You do not have to have everything in this chart memorized, okay? But again, I'm giving you the information because the more you do understand it and see it, the easier the other questions are going to be, all right? So we have here, we have circles. We have limicons. Anybody in here in French? Or can anybody tell me what that fancy C is called? Nobody ever knows. I don't either. I want somebody to actually tell me. We have roses, and you can see why they're called roses. Then we have this, which I've heard pronounced limniscate, but I don't think that's right because the majority of what I hear is limniscate, so it rhymes with limp biscuit, limniscate, and that's what's happening there. And then spirals of Archimedes. So let's go through and talk about each one of these. When we start with our basic circles, R is equal to sum A times cosine of theta. So what is A? A is the diameter of the circle right there. That is A. So that diameter is 5, which means this one would be R equals 5 cosine theta, because they already told me it was cosine. So this one is also 5. That's A. How do I know it's 5? Because I counted. I'm being serious. I mean, I counted. It's 5. So then R here is equal to negative 5 cosine theta. We're going to look at how we know if it's cosine or sine if they don't tell us in just a second. This is A, again, which is 5 again. So it's R equals 5 sine of theta. And then here we have A, and R is equal to negative 5 sine theta. Yes, so let's look at that. So I want you to look at these. Well, and so it basically told us that too. It said A is greater than 0, A is less than 0, that type of thing. But I want you to look at where the circles are, because this is a huge piece that if you know this little tiny fact is going to really make some of these questions super easy for you. So in the unit circle, is cosine X or Y? X. Okay. So if you look at this, when this is positive and we have cosine, the center of this circle is on the positive x-axis. When A is negative and it's cosine, the center of the circle is on the negative x-axis. Now, also remember that with polar grids, technically we only have a polar axis, which is like the positive part of the x-axis, but it's okay to think about it and refer to things as x and y because that's still how we're thinking and how it kind of makes the most sense to us. Totally fine, right? So then here, sine. Sine is y, right? So when A is positive and we have sine, the center is on the positive y-axis. And when A is negative and it's sine, the center is on the negative y-axis. Okay, you see how that works? Even when you get into BC and you have to do some other stuff with polar, nobody's going to make you graph them and make them beautiful. The most important part is where is this graph and what is some more of its properties type of thing. So you just being able to recognize if it's sine or cosine is going to help you greatly with these multiple choice questions. Okay, we good with that? So let's look at the limicons. So with the limicons, we have some extra pieces here. So this is a limicon with an inner loop. See how this has a little loopy thing in there? So this right here, to find that part and what that length is, this is B minus A. And this part, the big distance here, is B plus A. And if we look at the general equations for limicons, I still have this part right here like I did for the circles, but I have something being added to it, which in the rectangular coordinate system is just a vertical shift. Totally not what's happening here, all right? So we have this relationship, A over B is less than 1, which also means that A has to be less than B. It's another way to look at it. Again, not something you have to have memorized, but we're just looking at how these all relate to each other. So in this particular case, do you think that this function would be a sine or a cosine? Cosine. And positive or negative? Positive. Okay, see, that's something there. So R is equal to, so I need two numbers that are going to subtract to give me 3 and add to give me 5. So that's 1 and 4. So this is going to be 1 plus 4. And we already decided that it is cosine theta. Okay? We good with that? All right, so then we have, so that's when A is less than B. Well, if A equals B, we get a cardioid. And so this length right here is technically still A plus B, or 2B, but really 2A is usually how it's referred to, because A and B are the same. So I would need half of that. If that's 5, half of that is 5 halves. Do you think this is sine or cosine? Sine, positive or negative? Negative. So this is going to be R equals 5 halves minus 5 halves sine of theta. So we had A less than, yeah. This length right here is 2 times A, and that's 5, so it's half of 5. Yeah. So this is like specifically for this specific graph. I mean, it could be anything for any graph. As long as A is equal to B, that could be anything. But to graph this exact one, that's what the numbers would be. All right, so then we have a dimpled limicon. So I want you to think about, let's say that we had a cardioid, so the little tip of the point of the heart, whatever that thing is called. If we start to pull it away from the pole, it looks kind of like a dimpled limicon. Like this really is trying to be a heart, but you just can't get there. You see how it looks like it's pulled away some? And so this part here, this is A minus B, and this part right here is A plus B. So there's a little part to the right here. This is A minus B, and then the left-hand part's A plus B. Mm-hmm. Always B minus, because you're going to have two numbers. You got to subtract them to get the little one and add them to get the big one. Do what? It's from the pole to the function right there. It's the length of 1. So B is less than A, which is less than 2B. So here A is greater than B, but it has to be less than 2B. Do you think this is sine or cosine? Cosine, positive or negative? Negative. See how you already know stuff about polar? And like that's a huge thing to know, like very important thing to know. So R is equal to, so I need two numbers that subtract to give me 1 and add to give me 5. 3 minus 2 cosine theta. We good so far? All right. So then we have a convex limicon, which kind of looks like a circle, but it's not. It's kind of a wonky circle, right? It's not really circular, but I know it really kind of looks like it is. It's kind of like if I took this dimpled limicon who's trying to not be a heart anymore and I inflated it some more, it would be this, which is just a wonky circle, okay? So we have still this part right here, which is the same as this. This is A minus B, and this part right here is A plus B. So here A would be greater than or equal to 2B. What do you mean the edge of each circle? I'm going to the red part, so I don't... Well, there's only one in all of them except the inner loop, yeah. Well, I'm going from the pole to the outside here and the pole to the outside there. And then do you think this would be sine or cosine? Sine, positive or negative? Positive. So R equals, need two numbers that are going to subtract to give me, what, 3, and add to give me 5? It'd be 4 and 1, yeah. So 4 plus sine theta. Again, the most important thing to get right now is just figuring out if it's sine or cosine. If we can do this and you can kind of follow along with the rest, we're good, okay? We good so far? All right, so let's look at the roses. So with the roses, I now have a number in front of the theta. That's my n. And I don't have a plus or minus like I did here. And it says if I have n petals, if n is odd, 2 n petals if n is even. So the number of petals equals n. If it's odd, you double it to get the petals if it's even. And again, we'll talk about that as we go through this. So since this says this is odd, and we have 3 petals. My n equals 3. Now, when we decide if these are sine or cosine, things change just a little bit. Now, I no longer care about the y-axis at all. I either have a petal on the x-axis or I don't. If I have a petal on the x-axis, it makes it cosine. If there's not a petal on the x-axis, it makes it sine. Okay? So there's a petal on the x-axis, plus they already told me, and this is a, and in this case, a is 4, because I counted. So r is equal to 4 cosine 3 theta. Okay. Then I have, for the next one, I have 4 petals, and so n gets doubled, which means n is 2. So I had to double n to get the 4, right? So n is 2, because that's what's in front of theta. I get 4 petals, because when n is even, you double n to get the petals. You don't double the petals. Yeah, you just divide it by 2. And then this is a. Do I have a petal on the x-axis? No, that's what makes it sine. Okay? So then r is equal to 4, because that's still a, times the sine of 2 theta. Okay. 5 petals, so the petals equals n, so n equals 5. Do you think this is sine or cosine? It's sine, because it does tell you. But also, we don't have a petal on the x-axis. So here, r is equal to 4 sine 5 theta. All right. Then we have 8 petals, which means n is equal to 4, right? And a is still 4. Do you think this is sine or cosine? Cosine, because I have a petal on the x-axis. I also have one on the y-axis, but I don't care. Okay? Don't care. So this is r equals 4 cosine 4 theta. Okay. Everybody good with that? All right. So again, identifying sine and cosine, huge part of that. Now let's go look at our lemniscus. So this part of the equation looks very much like this, almost like I should have a 4-petal rose. But this is the big difference here, r squared. A squared is also a big difference, but a is a number, so you don't always necessarily notice that it's squared, right? So here, this is a, and a is equal to 4 in this particular question. I know that this is cosine for the same reason that I do for the roses, right? There is a petal on the x-axis. That means that it's cosine. So this is r squared equals 16 times the cosine of 2 theta. Then, for the next one, I do not have a petal on the x-axis, which means that it's sine. This is still a, and a is 4. So r squared equals 16 times the sine of 2 theta. Okay. What questions do you have? All right, so then we have the spirals of Archimedes. Look at this equation. How is it different than all the other ones we did? Look at the equation. A theta. There's no sine and cosine, right? So it's r equals a theta plus b. And whether theta is greater than or less than 0 depends on which way it spirals, and that's the way a spiral of Archimedes works. Okay? All right, so this is a lot of information, right? And, I mean, it wouldn't hurt you to know it, but you don't have to absolutely go home and memorize all of this. Right now, understanding how to figure out if it's sine or cosine, that's our #1 goal. Bless you. Okay, we all good with that? Okay, so then we're going to stop here for today because I want to talk about our scores. We'll finish this up tomorrow, and I have another page so that we can do some examples.